Hello and welcome back. Section 2.3, we get into the properties of functions. So now that we can differentiate what is and is not a function, in this section we're assuming that we are working with a function. So we'll start with the parity of a function. Parity just means is it even or odd. It's also possible that it's neither even nor odd, but that's still under the headline of investigating the parity of a function. So we're going to let f be a function with domain D. F is even if, I'm going to show you another new symbol. Upside down capital A means for all. For all x in the domain D, opposite of x also in domain D. And here's the important part of it. F of opposite of x spits out the same value as f of x. So x and the opposite of x have the same output. If we take a look at what that would mean, if I take an arbitrary point here, and this is my x value, I go to its opposite over here, and the output would have to be the same. And that would happen at any pair of opposite points. I would have a function that was symmetric about the y-axis. So even functions are symmetric about the y-axis. That should kind of look familiar to what we did when we were just working with any equation and checking for just symmetry about the y-axis. So next up we talk about what it takes to be odd. So all x in the domain have an opposite of x that is also in the domain, and f of opposite of x spits out the opposite of f of x. Again, let's make just a quick rough sketch of what that would look like. So here's some input value x, here's our output value y, and when I go to the opposite of x, I get the opposite value, I get the opposite output. That would make us symmetric about the origin. We flipped over both axes. So even, symmetric about the y-axis, odd, symmetric about the origin. Now how we practice that with our equations. We'll start with f of x is equal to x to the 6 minus 57, and we're going to determine the parity. For the next few problems. So the first thing we do is find f of opposite of x. So opposite of x to the 6 minus 57. So f of opposite of x is, I have an even number of negatives multiplied together. That flips the coefficient back to a positive. So x to the 6 minus 57. So then I check. Does f of opposite of x equal the original f of x? Since this one is a yes, we can stop here and say that this is an even function. Next one, same question, but g of x is x to the fifth minus 4x cubed. First thing we do is find g of opposite of x if we're looking for parity. So opposite of x, close it up, quantity raised to the fifth minus 4, there's another x. New set of parentheses, fill them in with opposite of x. This time I have an odd number of negatives. Coefficient stays negative then. I have 1 here, 3 here, 4 negatives altogether. That'll make it a plus 4x to the third. So first thing I check, does g of opposite of x equal g of x? This time the answer is a resounding no. So then we take a look at what opposite of g of x looks like. So that would be the opposite of the quantity x to the fifth minus 4x to the third. And we have a little bit of simplifying to do on that right hand side. We'll distribute that, make that opposite of x to the fifth plus 4x to the third. Now we do another check. Does g of opposite of x have the same output as opposite of g of x had? Well, here is g of opposite of x. Here is opposite of g of x. Same. All the way through. Opposite of x to the fifth plus 4x to the third. Yes, so this one is an odd function. So I'm going to have you try h of x and k of x. Test for parity. So go ahead and pause the video, give those a try, and then we'll finish those together. Okay, welcome back. So h of opposite of x, 4 times opposite of x, close it up, 7th power is outside, plus 3 times opposite of x, quantity to the 8th. H of opposite of x. I have an odd number of negatives multiplied together, so I have negative 4x to the 7th. Even number of negatives multiplied together, plus 3x to the 8th. H of opposite of x does not equal h of x, so we have to keep going. So then next, we'll find opposite of h of x. So that would be the opposite of the quantity 4x to the 7th plus 3x to the 8th. And just do a little simplifying on that. Opposite of h of x then, negative 4x to the 7th minus 3x to the 8th. Then I check, is h of opposite of x the same as what we just found? Opposite of h of x. And h of opposite of x, we had a negative 4x to the 7th, but then we had a plus. The opposite of h of x had a minus. They are not equal to each other. So this tells me that they are also not odd. So this is neither. Not even, it's not odd. K of x, we'll start with k of opposite of x. Absolute value of the opposite of x minus 2 times opposite of x, quantity squared. Opposite of the absolute value of x, think of it as absolute value of negative 1 times x. Well, that would give me the same thing as 1 times x in the absolute value. So k of opposite of x, it's the same as absolute value of x. And I have 1, 2, 3 negatives multiplied together. That'll stay a negative. So then we check, is that the same as the original? It is. So k of opposite of x is equal to k of x. Therefore, this is an even function. So we don't have to bother continuing on with the test of putting up opposite of k of x. If we found out it's even, you can stop the test. The function will never be both even and odd. Okay, so next we'll sort of do a little sketch of increasing, decreasing, and constant pieces of a function, and then we'll talk about creating a more formal mathematical definition for increasing, decreasing, or constant. So intuitively, we read graphs the way we would read a sentence from left to right. Anytime you're reading something in English, you're reading from left to right. That's the way we would interpret graphs as well then. So as we move from left to right, if the points are getting higher, that is an increasing interval. From left to right, if the points are dropping, then we are decreasing. And of course, if we are level and flat, function is constant on that interval. All right, so that's sort of the intuitive definition of it. This being a college level math course, they need you to know at least a little bit more about the formal technical definitions. As if you're in this course, you're going to be moving on to some higher level courses as well. So we'll consider an open interval I. So function f is, and we'll do just we'll do the increasing. Decreasing can be defined in a similar fashion. So function f is increasing on open interval I. So we'll make this our open interval. So from this x value on the left to this x value on the right, if for all x1 less than x2 on open interval I, don't let the notation scare you on this. If x1 is less than x2, that just means this point's on the left, this point's on the right. It's getting crowded there. I'll switch colors, make it a little easier to read. There's x1, there's x2. Then think to yourself, okay, if this is increasing, how do their outputs compare? In other words, f of x1 compared to f of x2. Well, as you can see, f of x1 is less than f of x2. So you should be able to write a very similar definition for decreasing. X1 is still going to be less than x2 on open interval I, only the outputs for x1 will be higher than the output for x2, of course. So then the next thing we talk about are local or relative extrema. So some authors use local, some authors use relative, some mix and match and just kind of use them both interchangeably. They do mean the same thing, so whatever other coursework and other authors you run across, I want you to be prepared to see either one of those. All right, so we'll start with a definition for a local maximum. Again, local could also have been written as relative. At point x equals c, if there exists a neighborhood around C such that f of x, if C is a local max, f of x is going to be at less than f of C for all x on this interval I. We'll just call it the neighborhood. So it's not guaranteeing it's the highest point in your whole graph. We might have something that looks like this as a graph. This point right here is a local maximum. It's not saying it's the highest in the entire function. It's saying that if I put a little box around this, that this is the top one in this little neighborhood around there. And you can write a similar definition for a local minimum. All right, so I'm gonna not put a scale on this, but we're just going to investigate some points. Let's see, so we'll start here. All right, so we'll call this point A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S. Okay. Local maxima. So that's the plural of maximum, would be maxima. A would not be considered a local maximum because A is an open circle. That means I can get close to it, but I can't touch it. And no matter how close in you get, let's say you're within 1/10,000,000th of a unit away from it, I can say, okay, cut that distance in half. Now you're within even closer. If you think that's close enough, cut it into quarters, cut it into 16th, cut it into millions. You can always get a little bit closer. So A is not going to be in our collection of local maxima. B is just an intercept. C is just an intercept. D, we bottom out there and turn around. That sounds like it's one of our local minima. E, again, just an intercept. F is a peak, so that is one of our local maxima. G, another intercept. H, we bottom out there, so that's one of our local minima. I, again, just an intercept. J is a top point. L, a bottom point. N, a top point. P, a bottom point. R a top point, S is neither, it's just an intercept. Global, also called absolute maximum and minimum. Just like it sounds. Now we don't care about making a small neighborhood around it where F is the top dog, or a small neighborhood around it where L is the lowest point. Now we're saying, okay, take a look at the big picture. What's the maximum in the whole picture? This one tops out at R. So R is both a local maximum and a global maximum. As far as global minimum, though, we keep dropping forever. There is no global minimum for this problem. All right, so we can also use graphing utilities to sort of approximate intervals where the function is increasing and decreasing and identify local extrema if they're asking us to, again, approximate these. So we'll use f of x is x cubed minus 7x squared plus 4x plus 3. And we'll try to find extrema and intervals where the function is increasing, decreasing, and constant. I'm going to try and keep this angle just right so you can see it but not have too much glare or shadow. So our y equals, we'll just clear out any older functions that we've got in there, key in the new guy. So x raised to the third minus 7x squared plus 4x plus 3. So we'll start on zoom 6, the standard window, the 10 by 10, or 10 in each direction graph. As you can see here, this should be a continuous function, but it dips below where we can see. We know that that's happening, it looks like somewhere around 3, 4, or 5. So we can go to our table set, start at 0, we'll change by ones this time, and the independent will have on auto. So it'll think, so it looks like we go down, negative 29 is sort of the lowest one that they mention. So we'll go a few beyond that. It looked like our x's were doing okay where they were. So our x's we'll leave alone, negative 10 to 10 on a scale of 1. Y min, we'll drop that down to maybe negative 35, give or take. Y max seemed fine at 10. We'll count by 5s this time. Okay, so now we can see all those key turning points in our graph. So if I want to know where those are, I can have the calculator calculate it for me. Second and calculate. Back to that menu. This time we're looking for, we ran across a maximum first, so we'll select option 4. And same idea as the intercept, only now we want to be to the right and left of this point. So left bound, I'll move a little bit to the left. Right bound, arrow to the right until, yes, we're definitely to the right of where that peak is, and then a guess at where it is. I'll get the cursor in relatively close. It'll think for a minute, and there's our ordered pair. And again, we'll round to the nearest hundredth for this one. So 0.31 for the x. And the y's 3.60. Again, we round instead of truncating. So that ordered pair is our local maximum, local minimum. Same kind of idea. Go into your calculate menu. So second and calculate. We want this time the minimum instead of the maximum. And we're going to get close to this valley here. Just to the left of it. Just to the right of it. And a reasonable guess at it. It'll think for a minute. And again, nearest hundredth. So 4.36 for the x. And negative 29.75 for the y. So these are ordered pairs for a local maximum or a local minimum. Next, they may ask us about intervals where this is increasing, decreasing, or constant. We'll start with increasing. We don't have to do any more calculations on here now that we know where those two key points are. There we go. Just found the sweet spot there. So it looks like coming from the left, we're increasing until we hit that maximum. So our x's go from negative infinity up until we hit our local maximum at 0.31. They're not the only places where that graph is rising, though. From this valley to the right, we keep rising. So we'll union that with the 4.36. Again, if we know we're increasing, we know the y values are changing in the positive direction. It's saying where on the x-axis is that happening. So 4.36 approaching infinity. And in between, the graph was dropping. So we're decreasing from x is 0.31 to x is 4.36. So even though this one looks like an ordered pair, it's not. This is an x value, this is an x value. A pair of x values, it's an interval, not an ordered pair. All right, so then the next thing we look at is the idea of the average rate of change of a function. Average rate of change of a function, we would just do f of b minus f of a over b minus a. And here a and b are not the same since they're in a denominator. That setup should look familiar though. A couple of y values subtracted over a couple of x values subtracted. That is the idea of slope. When we were working just with lines, though, the rate of change was the same everywhere. Rate of change between these 2 points was the same as the rate of change between these 2 points and any other combination of them. It was changing at the same rate everywhere. Now that we have these curves, rate of change between this point and this point would be a negative since it's dropping. Rate of change between, say, this point and this point would look like it was 0 if it was more flat, and between here and here it looks like we would have a sharp positive slope. So it's basically saying, okay, we know it's a curve, but on this interval, what's happening overall? What's happening on average? Hence the name, average rate of change. So we'll look at f of x is x squared minus x plus 1. And we'll find the average rate of change. We'll start on the closed interval 1, 4. So f of 4, we have 16 minus 4 plus 1, so that is a 13. F of 1, we have 1 minus 1 plus 1 is 1. So our average rate of change, our outputs over our inputs. And as long as you're consistent with these, it doesn't matter the order. Whatever output you pick to go first, its buddy has to go first. The input has to go first at the bottom. That corresponds to that. So we have 12 thirds, which is an average rate of change of 4. And let's see, next we'll try on the interval 1, 2. So we already know what f of 1 is. F of 2, we have 4 minus 2 plus 1, so 2 and 1, 3. Average rate of change there, then 3 was my output minus my old output of 1 over our, let's see, 3 minus, f of 1 was 1, and then over the x corresponding to the 3 was a 2, x corresponding to the 1 was a 1. Average rate of change of 2 then. Now, this is one of the ideas that you investigate quite a bit more once you hit either business calculus or Calc 1, whichever route you're going. But the idea is, if we have some curve and I want to know the average rate of change, I can pick any 2 points, but I'm going to get more and more accurate of an idea of what's happening the closer I slide those 2 points together. The more these guys get together, the closer I get to finding out what's happening at exactly that 1 point. The idea is you get close to, instead of an average rate of change, eventually in calculus you'll look at what's called an instantaneous rate of change. So that's just an idea that's coming up. So next we'll look at the idea of a secant line. And what we drew there on that last sketch, those were secant lines, just the lines connecting 2 points along a curve. The slope of a secant line is the average rate of change. And then we just do the equation of a line from there. So let's do the secant line for, we'll keep that same function from before. F of x was x squared minus x plus 1. And we'll do the secant line for the interval 1, 4. So recall that f of 1 was 1 and f of 4 was, let's see, 6 minus 4, 13. So basically all this is saying is you have these two ordered pairs, write me the equation of a line. So instead of saying m equals, we'll just say average rate of change equals. So 13 minus 1 over 4 minus 1. That's our 12/3, which was that 4 we saw on the other page. And then we'll just do change in y is average rate of change times change in x. So y minus 1 is equal to 4 times x minus 1. So y minus 1 is 4x minus 4, so y is 4x minus 3. So there's our secant line. So let's just take a quick look at what that looks like in the graph. Let me get rid of this older function, and we'll put in our x squared minus x plus 1 into y1, and we'll put our secant line of 4x minus 3 into y2. And our window, I'm not interested in just anywhere. My x's went just from 1 to 4. My y's just went from 1 to 13. We'll set the scale back to a 1 for the y's. So then I'll graph that. So that shows me the curve of that square function, and then this shows me that secant line that is approximating what's happening between those 2 points on the curve. All right, so some problems to try out. This was section, remember, 2-3. I would try 1 to 63, the odds. 79, 85, and if you're looking for some challenge problems, 87 to 101 asks some interesting questions. And that's the challenge ones are optional, just if you're looking to really sort of test yourself and see some of these concepts a little bit deeper. All right, if you have questions, get in touch. Otherwise, I will see you next time.